Welcome to the lecture on the third module of functions of several variables. We now touch upon one of the most critical concepts of differentiation, that is called the Jacobian. The Jacobian is a concept that arises whenever we seek a change of coordinate systems. If we desire to move from one coordinate system to another coordinate system, and let us say we are performing a double or triple integration operation, then we need to introduce the Jacobian in order to equalize the outputs of the double or triple integrations in the original domain and the outputs of the double or triple integrations of the new domain. Now, basically, the Jacobian has to be understood at a lower level through a linear transformation. Suppose we move from one coordinate system to another coordinate system using a linear transformation. So if you have a domain D in the original domain, original coordinate space with a certain area delta A, and then we map it on to a new coordinate system using the linear transformation, then there are two possibilities. One possibility is the region undergoes an expansion, so the area element also will expand in comparison with the area element of the original domain, or it could contract. So when you perform a double or triple integration operation, the Jacobian is needed as an equalizer for the output. But not all transformations will be linear transformations. They could also be nonlinear transformations. So overall, the essence of working on Jacobians is to apply them to contexts like performing double and triple integrations in order to equalize outputs of a certain physical calculation in the original domain or in the transform domain. Normally, we seek a change in the domain whenever the problem is difficult to negotiate in the original domain, which would hopefully become very simple when we transform. So the Jacobian is basically a determinant, obviously should return a real quantity. Now, when we have a transformation of u and v in terms of x and y, then we get a 2 by 2 determinant with columns with rows as dou u by dou x, dou u by dou y, dou v by dou x, and dou v by dou y. You could also arrange these in columns because the determinant does not vary when we arrange it in rows or in columns. So the Jacobian of u and v with respect to x and y is a determinant. Similarly, there could be transformation from a three variable space to another three variable space, u, v, and w in terms of the variables x, y, and z. So in which case the determinant will be a 3 by 3 determinant with the partial derivatives of u, v, and w in terms of x, y, and z arranged in rows or arranged in columns. So it's a very, very straightforward approach to find the Jacobian. Now there are a few properties which we look into. One is what is we call the inverse law. If J1 and J2 are the Jacobians of u and v with respect to x and y, and x and y with respect to u and v, then their product is equal to 1, provided none of the Jacobians J1 and J2 vanish. So this can be used to calculate J2 in terms of J1 as a reciprocal or J1 in terms of J2 as a reciprocal. Then comes the chain rule. If u and v are functions of x and y, and further x and y are functions of r and s, then dou uv by dou rs will be dou uv by dou xy into dou xy by dou r and s. So this is what is called the chain rule, with x and y being called the intermediate variables. One of the main takeaways of Jacobians at a higher level is to find use the Jacobian to find out derivatives of implicit functions. So this particular rule, dou u v w by dou x y z, can be obtained in terms of ratio of partial derivatives. The sign would depend upon the number of variables we are connecting. Because of an odd number, so you can see -1 whole cube. So this can be a very valuable tool in order to find out dou u v w in terms of dou x y z. Now, there are some well-known uh, problems that arise when we talk about Jacobians. The first problem is when we transform from Cartesian coordinates to polar coordinates on the plane. So all of us know the geometry behind the polar coordinates in a plane. That will give us x is equal to r cos theta, y is equal to r sin theta. And then we can find the Jacobian dou uv by dou xy by dou r theta, and we get it as r. The details are shown in the solutions. The second example relates to cylindrical coordinates. All of us know x, y, and z, if they are Cartesian coordinates of any point on a cylinder, I mean a circular cylinder, then the corresponding polar coordinates will be r, theta, and z on the cylinder, and they are connected by x is equal to r cos theta, y is equal to r sin theta, and z is equal to z. So we will show that Jacobian is also equal to r. Then thirdly, we have transformation from Cartesian coordinates on a sphere to its spherical polar coordinates. So x is equal to r sin theta cos phi, y is equal to r sin theta sin phi, and z is equal to r cos theta. These are the transformation equations. So let us go through each one of them step by step. The first problem is to find the Jacobian when we transform from plane polar Cartesian coordinates to polar coordinates. So dou xy by dou r theta, as already explained, is a Jacobian with rows dou x by dou theta, dou x by dou r, and dou x by dou theta, dou y by dou r, dou y by dou theta. So get the partial derivatives, and then you get on expansion r is a Jacobian. Similarly, when we talk about the cylindrical system, the Jacobian gives us r. You have to be watchful with the third row, because the third transformation equation is just z is equal to z. It does not depend upon r and theta. Hence, you can find those zeros in the first and second places in the third row. And the third one is a little bit intense. So you'll have to work out the partial derivatives of x, y, and z in terms of r, theta, and phi, and then plug in into the Jacobian rule, and then careful manipulation using your fundamentals of trigonometry will give us r square sine theta. So these are the three very famous Jacobian results, which will be using in working out double and triple integrals. Question number 2 is very straightforward. U, v, and w are functions of x, y, and z, and we want the Jacobian of u, v, w with respect to x, y, z. So find out all the 9 partial derivatives, plug into the determinant rule, and you get some 10x plus 4. That's the Jacobian. The third one requires a little bit of manipulation before you can work out the Jacobian. U, v, and w are expressed in terms of x, y, z, but we need the Jacobian of x, y, z in terms of u, v, w. Therefore, you have to do some reverse engineering and find out x, y, and z in terms of u, v, and w. That will take a bit of time. And once it is there, you can easily find out the partial derivatives of x, y, z in terms of u, v, and w. Plug in into the Jacobian rule that you can see, and then careful expansion, simplification will give you u square v. Problem number 4 has been selected to establish the j into j dash is equal to 1 inverse law. So x and y are functions of u and v, therefore you can find out j, which gives us 2u by v. But in order to find out j dash, you have to do some reverse engineering and transform the given equations to express u and v in terms of x and y, and that has been shown in detail. So we have u square is equal to xy and v square is equal to x by y. Then you find out your dou u by dou x, dou u by dou y, dou v by dou x, dou v by dou y. Plug in into the Jacobian rule, and then you get v by 2u, and you can actually see j is already 2u by v, therefore that product will give us 1. This is another example where we are testing the chain rule, jj dash is equal to 1 from Cartesian to plane polar coordinates. So finding out j is straightforward. Already it has been shown to be r, but in order to find j dash, r and theta had to be expressed in terms of x and y, which is shown in these steps. And once you have r and theta in terms of x and y, you can easily find out j dash using the Jacobian rule, and then establish j into j dash is equal to 1. Then 6 is a straightforward problem. U, v, and w are functions of x, y, and z, and you have to establish the Jacobian is 4. So you only have to be good in partial differentiation. So I hope students are familiar with these operations. You plug in the 9 partial derivatives into the Jacobian format, and then you get desired result 4. So you can have a few problems for your own practice, but Jacobian mainly has to be understood as a very important tool when we work with double and triple integrals. And that is happening whenever we want to transform the given problem in a domain where it is difficult to solve to a new domain where things hopefully become easy. So this is about Jacobians and how it should be applied as a very important tool.